Today we're going to talk about derived functors. Last time we introduced the derived categories, and derived functors are basically the functoriality statement about the derived categories. We'll have to distinguish between left and right right derived functors, and we will give explicit formulas for how to compute left and right derived functors. In the case where this is usually discussed in sort of abelian categories with enough projectives or injectives, we'll see how this recovers the usual notion, but our discussion will be slightly more general. And towards the end of the lecture, we'll have a long explanation of how derived functors relate to the abstract concept of Kahn extensions and adjunctions in infinity categories. The second part is not necessary for the rest of the course, so if you already know this or you want to take adjunctions and Kahn extensions as a black box because you know it from ordinary category, you can safely skip this part. Hi, I'm Thomas Nikolaus from Mathematics Münster. Let's recall that we have introduced in the previous videos the derived category of an abelian category. So the setup was that A is an abelian category. And in this generality, we've introduced the derived category. And we will override in this course the usual derived category, which usually means the homotopy category, the triangulated category. For us, the derived category is always an infinity category. And that was defined as we took this category Ka. By the way, I believe D stands for derived and K for complex, I think. It's German for complex, I guess. And so we have universally, in the sense of via Kahn localization, inverted the quasi-isomorphisms. So that is an infinity category, and it turned out it had finite co-limits and finite limits, and some very nice properties. And now today we want to discuss the functoriality of this construction. So assume that f is an additive functor between abelian categories. Functor. So what is an additive functor? So probably most of you know this notion, but let me say it anyway. This means it sends the zero object to zero, and it sends direct sums to direct sums. And I'm writing this in the usual sloppy way, but really this means that it sends, say, the direct sum is a coproduct and a product in an abelian category, so it sort of sends products to products, or equivalently it sends coproducts to coproducts, right? This is not an abstract iso, but this is a map we always have, say, from here to there. And this is an equivalent. So that's a property of a functor. It's not extra structure like in the symmetric Noidel case. That's what I'm getting at the moment. But what we don't want to assume that this is a functor, an exact functor. It's not necessarily compatible with the additional structure supplied by an abelian category. It's just an additive functor. And based on that, we can get an induced functor on the categories Ka and Kb as follows. We first get an induced functor chain A to chain B. It's just a level-wise functor, maybe I call this chain F. And what does this do? This will just send a chain complex, C0, C1, and so on, will be mapped to the, just apply the functor level-wise. Fc0, Fc-1, Fc1. And I'm using here homological grading conventions, and all chain complexes are unbounded. And this is obvious because, I mean, the only thing you need to check is that the square of the differential is 0 again, but because f sends 0 to 0, it sends a 0 morphism to a 0 morphism, and that is again a chain complex. So that is a functor. And recall that in order to define the category Ka, we have leveraged an extra structure on this category of chain complexes, namely that it's enriched over chain complexes of abelian groups. And it turns out that this functor is actually an enriched functor, which is an enriched functor. Enriched functor. Right? In other words, it induces also chain maps on the chain complex of maps between two objects here and the chain complex of maps between two objects there. And this is basically immediate from the fact that it's an additive functor. If you just write down the formula for the chain complex here and the chain complex here, then you see that you get an induced functor. I mean, the chain complex there is basically a big product of maps and with a specific differential. And then you see that you get an induced map here. So from any additive functor, we get such an induced functor, which is an enriched functor over chain of abelian groups. And as a result, we can just get an induced functor on this K categories. Namely how? So we have this Ka, and this was defined to be the DG nerve of this category chain A, of this chain enriched category. Remember, the DG nerve was formed by first considering a category enriched over chain complexes of abelian groups as a category enriched over simplicial sets, where from a chain complex I get a simplicial abelian group, and then I forget down to simplicial sets, and then I form the homotopy coherent nerve of a simplically enriched category. And since this was actually Kahn enriched, then we see that this is an infinity category. Let me just mention that in the literature, you'll also find slightly different but equivalent models for the DG nerve. So there are more direct ways than going through simplicity enriched categories, but those categories will all end up being equivalent as infinity categories, so it doesn't really matter which one you use. Although in practice you might prefer a smaller model. Okay, but now the point is this DG nerve obviously gives an induced map. Maybe I write NDG of this functor f, which gives a map into the DG functor, a DG nerve of chain B, and that is KB. So we get such an induced map, and maybe we call this K of F. This whole map, Ka to B, KB, will be denoted K of F. Okay, so we get an induced functor, and the claim is that this functor, which commutes with finite limits and co-limits. Okay, so why is this true? Well, first of all, in order to check that it commutes with finite limits, say, we have to check that it preserves the terminal object, but the terminal object is 0, and this functor obviously sends 0 to 0. And then we also have to check that it commutes with pullbacks, but pullbacks were basically given in terms of a direct sum and then a certain cone. And this is also obviously preserved because the functor was additive. This functor obviously preserves direct sums, and then the cone was basically the direct sum of complexes with a funky differential. And that will obviously be preserved here. So this functor preserves finite limits and co-limits. Another way of saying, one way to say that is people usually say that it's exact if it preserves finite limits and co-limits. Okay, so that's a construction of this functor K of F. And now we would like to get an induced functor df from dA to dB such that, the most naive thing you might want to do is such that the square commutes. You just have Ka to Kb, and then I have my projections here. PA, PB, and maybe projection is a terrible word, but it's just the universal functor from Ka into its via Kahn localization dA in dB. The reason I say projection is because, of course, these have somehow the same object, so this functor is essentially surjective. So that's why I think of it as a projection, but maybe this is not necessarily a good way of thinking, because somehow this Dwyer-Kahn localization is like localizing a ring at an element. So this is maybe don't want to call this projection. Anyways, and you want to say such that we have such a commutative square is a commutative square in cut infinity. And so in other words, we have an equivalence between PB after KF and here DF after PA. And right, so again, I mean, such a square being commutative is extra datum and not just a property, but I'll keep that implicit as usual in writing such a square. But note, I only want this to commute in cut infinity. I'm not requiring any point set commutativity property. And now at this point, one is inclined to use the universal property of the derived category. So in order to, I mean, the universal property of dA tells us that functors df such that this square commutes are essentially the same as functors out of here to dB, which send weak equivalences to equivalences here. So in other words, what you need is that PB after KF sends weak equivalences here, which are quasi-isomorphisms to equivalences here. And at this point, I want to propose the following little exercise. Check that the following three assumptions are equivalent in our setting. First, there exists such a functor df making this square commutative. Secondly, kf sends quasi-isos to quasi-isos. So note this is not, I mean, you have to check actually a certain saturation condition for equivalences for this PB for that. And thirdly, and that's the most important, the initial functor of abelian categories is exact. So in other words, it preserves fibers and co-fibers, or I should maybe say kernels and co-kernels. It's left and right exact. And of course, this is a very strong assumption on our functor, which we might not want to make in general. So this exercise is meant to tell you that it's too optimistic to hope for such a commutative square. Right? In situations where our functor, I mean, unfortunately, or maybe fortunately, not all reasonable functors that we care about between abelian categories are exact. You know, like tensor products or HOMs or functors of this sort tend to not be exact. They're usually left or right exact, but not exact. And as a result, we can't implement this strategy of producing a functor, making the derived category exact. And we will now discuss how to remedy or how to account for this problem. So we've seen that it's too optimistic to hope for a commutative square like this, where we have kf, we go to kb, pb, a commutative square like this. So the next best thing that comes to mind is that you want to produce a square which doesn't commute, but which almost commutes. So maybe where we have a natural transformation eta like this. And then produce a functor like this. And of course, this is easy to produce such squares. You could, for example, let LF be the zero functor. Then you always have a natural transformation from zero into any other functor. So this is maybe not a super smart thing to ask for, just a square like this. But what we want to do is we want to say it's universal. It's kind of the largest possible functor in some sense that satisfies this. Or largest in the sense of category theory. It's terminal among all such squares. And that's what I want to make precise in the next definition. So the left derived functor LF of f is given by a functor LF dA to dB together with the transformation, a natural transformation eta as in the square, so from LF after PA into PB after KF, such that, so having a functor LF in a natural transformation is just what I depicted with this square here. And now I want to say it's terminal with respect to functors which have such a natural transformation. And in order to express that precisely, I say for any other functor h from dA to dB, the map, what I can consider as a mapping space in the functor category from dA to dB, h into LF, so map from this functor h into my left-derived functor. And from this I can produce a map in the functor category from Ka into dB. And now I want to say from h after PA. So the first thing you can do is you can pre-compose with PA. So that will produce a map into the mapping space from h after PA into LF after PA. But then I can post-compose with eta. And that gives me a map into the mapping space PB after KF. And I want to say that this is an equivalence. So note, this is the space of all choices of making the square where I put h instead of LF such a square. And then I'm saying this is the same as giving a map from h into LF. That is the statement that this is a terminal such square. Okay, so that's the definition of the left-derived functor. And I want to immediately issue a warning. The first warning is that I'm using the usual abuse of notation. I'm saying the left-derived functor, where I should maybe say a left-derived functor. But it's very easy to check that if the left-derived functor exists, then it's uniquely determined by the universal property, the usual yoga of universal properties. And by unique, I mean, as usual in this higher categorical setting, unique up to contractible space of choices. So if you want to get used a little more to universal properties, feel free to pause the video and check that. But I'll take that for granted at the moment after we have worked a little bit with universal properties. But I want to issue a more serious warning, is that the left-derived functor might not exist. Not exist in our generality. So if we just have abelian categories A and B without further assumptions, this functor just might not exist. And this is not just an academic warning. This actually happens in practice. It turns out, actually, we'll see in a second, we'll give a formula for the left-derived functor, which also implies the existence in a lot of situations. Like, for example, if one has enough projective objects. In general, it might not exist. It will turn out that it's a sort of limit, and so pretty much the same way that limits might not exist, it turns out that the left-derived functor might not exist. So that's a warning. And let me immediately state one little proposition, whose proof I will leave as an exercise. If LF exists, then it sends finite limits, or it preserves finite limits and co-limit. finite limits and co-limits. So for this, you just have to remember basically how finite limits and co-limits in dA and dB were computed. I leave this proposition as an exercise. So this is maybe one warning. Maybe you might want to include this property if you think of these categories dA and dB. I mean, we haven't talked about this, but these are the prototypical example of stable infinity categories. You might want to sort of consider morphisms, only morphisms which preserve finite limits and co-limits. But in this setting, I'm not saying that, but it follows automatically. Okay, so that is this little exercise. And now let me maybe put the definition of derived functors a little bit into perspective, because that will make it somewhat easier to discuss the abstract notion of derived functors. So, and that is the generality is Dwyer-Kahn localization. Given an infinity category C with a class of weak equivalences W, then, and a functor G from C into any infinity category D, then the left derived functor LG is given by the terminal triangle. So I want to say I have C, I have my functor G to D, and here I want to go to the Dwyer-Kahn localization. Remember from Achim's last talk, this always exists, possibly in the world of large infinity categories, but we didn't make that size issues too prominent anyway, so let's say it always exists. And then we have LG here, and we want to say it comes with a universal transformation. And maybe in order to state that universal property again, note that by the universal property of the Dwyer-Kahn localizations, functors from here to D, LG, can equivalently be considered as functors from C to D that send weak equivalences to equivalences. So one way to say that is that I can consider eta as a natural transformation from LG into G, where now I consider LG as a functor also defined on C. And I will implicitly do that here. So, and then the universal property reads as follows, such that the induced map maps H into LG, eta upper star maps H into G, and this now all is the mapping space in the functor category, is an equivalence for each H from C W to the minus 1 into D, or equivalently considered as a functor from C to D, then that sends weak equivalences to equivalences. And note the universal property of the left derived functor between derived categories is just a special case of that, where I just go from Ka to dB. So this is my functor G in that case, and then I left derive it to become a functor like this. And I mean, you see, so I've basically left all these PA, PBs and this stuff implicit in this definition. But that is useful in order to get control over the notation. And there's the second part of the definition of the left derived functor I want to give. We say that LF, and I should really say the pair consisting, LG and eta, but by the usual abuse of notation, I'm leaving the eta implicit. We say that LG is the absolute left derived functor, if for any further functor t going from D into any other infinity category E, the induced triangle which is C to D, I have my G here, and I can post-compose with a T, go to E. And then here I have C adjoint W to the -1. And then I actually can also post-compose my LG with T, so T after LG. And then I get an induced transformation T after eta. Right, so I just take this triangle here and whisker it with the functor from D to E, such that the induced triangle exhibits, I mean, it's still a left derived functor triangle, exhibits T after LG as the left derived functor. Of T after G. So, and note that, of course, I mean, T the identity is allowed. So every absolute left derived functor is in particular a left derived functor. So in that sense, we consider being absolute left derived as a further property of a left derived functor. It basically says that it base changes well. And some authors will only allow those as left derived functors. And in fact, we will see later that, I mean, in fact, this is really the useful case. Maybe I should underline the absolute as well. For example, if you want to produce stuff like the Grothendieck spectral sequence and so on, you'll need this kind of base change behavior. And we will also see criteria in a minute as to when a left derived functor exists and when it is an absolute left derived functor. But it turns out for our discussion it is actually useful to also have the notion of left derived functor, not the absolute one. That's why I introduced this terminology here. And of course, we will also apply this absolute terminology to derived categories. If we have this functor from Ka to Kb, then we also talk about the absolute left derived functor. And again, this is a property, just taking this back to the example we started with. Okay, so that is the notion of left derived and absolute left derived functor. And of course, I mean, I could repeat my warning. The absolute left derived functor even exists way more rarely than the left derived functor. I mean, there are a lot of situations, we will see that in a second, where the left derived functor exists, but it's not absolute. And so, let me give you one immediate remark though. And that is, the thing I already used implicitly was that the functor category C adjoint W to the -1 into D is equivalently described by the universal property as functors preserving weak equivalences C into D. And then this can be naturally considered as a full subcategory of C to D. And the left derived functor is some sort of co-reflection from here to there. So I'll write that in a second, but what you want to do is you start with a functor here and you want to produce a functor in this full subcategory. And what you're doing is you're doing this in a co-reflective way, in a universal way. So for given F a G in fun CD, we have that LG by definition was in the subcategory and maps from any functor in the subcategory into LG is equivalent to maps H into G. I'm just restating the universal property for H in the subcategory. But here you very clearly see that this is some sort of co-reflection onto the subcategory. And we will, I mean, this is actually what is called a right adjoint of the inclusion, and we'll talk about adjunctions in the next video. But I guess at this point it's kind of roughly clear what that would mean. Maybe taking clues from the ordinary category case. And note there's one thing which is always confusing. This is what would be called the right Kahn extension. But it's called the left derived functor. So there's this totally confusing sort of opping going on. Left derived functors are sort of right Kahn extensions, whereas right derived functors are left Kahn extensions. So just as a warning, this always confuses me. I hope it doesn't confuse you now that you have this warning in mind. Okay, so now here's the main theorem that we want to prove in today's lecture, or that we want to discuss at least. The following theorem: for any functor g from Ka into D, where D is an arbitrary infinity category, no assumptions on D, no assumptions on the functor, we have that the left derived functor of G evaluated on an object C in Ka, so chain complex, is given by the inverse limit over all C hat to C, G of C hat. Maybe I erase this arrow. This is just meant to indicate that this is a filtered, co-filtered limit. So provided that this limit exists for each C in Ka. And of course, this is the same kind of limit that you've seen in Achim's last lecture when he computed the mapping space in the derived category. And so this limit is really a limit over the slice category. So we have Ka, we slice over C, and then we take the full subcategory of quasi-isos. That was the notation used in the last video. Okay, it's a limit over this category, and again, I guess we're using implicitly that this functor can be extended. I mean, this is obvious. We just extend it to this category by just going from Ka, quasi-iso to Ka, a source object, and then to D. Okay, good. So that is the statement of the theorem, and let me immediately start giving a bunch of examples. So, example. So the first example is the following. So for C equals 0, so I have the 0 object. So what is the derived functor? So let's compute the left derived functor, and I guess now let's make the assumption that all these limits exist in the target category, so that this formula applies. So now let's compute what the left derived functor evaluated on 0 is. So by definition, or by this formula, it's now the inverse limit of C hat over C over 0, quasi-isomorphic objects which are quasi-isomorphic to 0, these are also called quasi-acyclic, of G of C hat. But now I claim that this is just G of 0. And why is this? Since I claim in the slice category 0 is an initial object. 0 is initial in Ka Qi over C over 0. Right, and we've seen that if you have an inverse limit and the indexing category has an initial object, then the limit is just given by the evaluation at that initial object. I think probably we've seen that in the dual setting for co-limits and terminal objects, but this is the statement here. And it's basically obvious that 0 is initial in that category. Let me leave that as a little exercise for you to check. Now let's take it a step further. For any C, assume that there is a projective resolution. So there is a k-projective object C hat with a quasi-isomorphism to C. So that's what you would call a projective resolution. And then we claim that this morphism, I guess maybe let's call this P, that P is initial in Ka quasi-isomorphic over C. And so to see this, we note that for any object, I guess I'm running out of letters. Let's say D quasi-isomorphic to C. Is this terrible notation? Maybe it is. So maybe let me use the C double hat notation, which might be even worse. Okay, for every other object, the mapping space. So in order to check that it's initial, we just have to show that for any other object, the mapping space is contractible. So we're just computing the mapping space in actually Ka over C. So this is, Ka quasi-isomorphic over Z was defined to be a full subcategory of Ka over C. So we have to compute the mapping space from C hat, C into C double hat into C. And now I'm invoking some general formula for the mapping space in slice categories. This is given by the fiber, so in other words, the pullback of the mapping space in Ka from C hat to C double hat. And from such a morphism from C hat to C double hat, I can produce the map in Ka from C hat to C. Sorry, I should write an arrow here, not a comma. C hat into C. And here I have a point. That is the object P. So we claim that this is a pullback in the infinity category of spaces. This is the general claim about how mapping spaces in slice categories look like. And now the point is, because C hat was k-projective, this means this functor C hat comma blank preserves quasi-isos in the second variable. Right? And this is a quasi-iso. So in other words, this means that this is actually an equivalence. And I guess, yes, so that's exactly the definition of k-projective. This is an equivalence. So in other words, this is an equivalence. Pullbacks of equivalences are equivalences. And so this means that this is actually, and note this is a pullback in the infinity category of spaces, not a sort of, I'm not claiming that this is always a pullback in the one category of simplicial sets or something. But anyways, this proves that this space is contractible, and hence that this is an initial object. And so maybe I squeeze in the conclusion at the bottom of this page. This means the left derived functor evaluated at C is just given, the co-limit over a category which has an initial object, the limit over this category with an initial object just given by evaluation on that object. And sorry for the confusion, I want to write LG. This is just given by G of C hat. So you see, we can compute this left derived functor, which is maybe given by this limit formula by just evaluation on a single projective object, or k-projective object. And this is why, in fact, this might not, of course, projective objects might not always exist. So many abelian categories that we care about in practice might not support enough and might not admit enough projective objects. And I mean, being k-projective is even a little bit more tricky. There you also have to take a filtered co-limit of over projective resolutions. So this might be an actual strong requirement. But note something more, and this is maybe note if for every object C there exists such a k-projective resolution C hat, then Lg of C is just given by G of C hat for any functor G. In particular, this also is compatible with composition, post-composition with functors T from D to E. Right, this formula given by evaluation is certainly compatible with post-compositions, i.e., in this case, every left-derived functor is absolute. Right, this is somehow, the left-derived functor can be computed out of purely diagrammatic reasons, just evaluation on any of those objects, and therefore it's actually compatible with all post-compositions. So this is actually one of the important special cases that one cares about in practice, of course, even though there are also cases where projectives might not exist, but if they do, then we can observe that this gives us absolute derived functors. Okay, so that was my first example, and really note that, maybe I should have said this as well, very often the formula I've now deduced from the abstract universal property, or at least my theorem, will be given as a definition of a derived functor. And this is, in my opinion, a little problematic for several reasons. I mean, the first reason might be that this is not obviously functorial. You might need to invoke some sort of functoriality of projective resolutions. But here you see somehow projective resolutions are functorial enough to give you an infinity functor. Like somehow it's kind of unique, but it's kind of built in the formalism that this gives us a functor. And it's not somehow something you have to invoke in order to produce the derived functor. And secondly, one might want to consider derived functors in more general situations. We'll see that next time, even in some non-abelian settings for non-additive functors. And that is certainly not super compatible with projective objects. And now let me give you a second example. And that is maybe the specialization to our original situation. Assume that f, a functor between abelian categories A to B, is additive, and maybe A is small. That means this one time makes this requirement. A is small and B, so from now again I'm going to drop that theoretic stuff afterwards again, and B has all infinite products. And they are exact. And this is, in Grothendieck's Tohoku terminology, that's a property AB4 star. So Grothendieck has this list of properties abelian groups can satisfy, ranging until AB5 and AB5 star, and this is AB4 star. And then the following follows. First of all, and this is a little exercise, that dB has all limits. This I want to leave as an exercise here. And I mean, roughly speaking, you just first of all think about what limits in KB are and then try to descend them to dB, the same way that we did for finite limits. The second statement is that immediately follows from that. In particular, it has inverse limits over these filtered diagrams that we had before. So the derived functor, LF from dA to dB exists. And finally, and this is something we already have seen earlier, that LF preserves finite co-limits. And limits. I guess I assumed A was small, so this is not going to have any co-limits or limits, so this is the best you can hope for, but we've already seen that this is always the case if the LF exists. And that is the sample application of the formula we had. And note here again, now we've deduced the existence of the derived functor without requiring any projective resolutions. And I mean, there's this little catch that I had to assume A was small, and of course, I mean, you want to really usually apply that to settings where A is really also large, and then, I mean, it comes down to a set theoreticality, but this is not somehow comparable to the non-existence of projective resolutions. Okay. Next example, or maybe before I say the example, I want to say that there's a dual notion of right-derived functors. Right, so right-derived functor, I mean, if I have a functor f or g from C to D, then the right-derived functor of g will come with a natural transformation, this time in this direction, and not from here to there, but there in this direction, i.e. eta now goes from, I mean, if I call that eta again, now goes from g to rg. If I again implicitly consider that as a functor also defined on g, and it has a dual universal property. I mean, and this can in fact be just deduced by applying the formalism to opping the whole functor. So you can just, then the dual of our formula, right? So we used that Ka is actually equivalent to, Ka op is equivalent to Ka op. So you can literally just apply our formula to the opposite category, get a dual formula, reads as the right-derived functor of g evaluated on some object c is given by the co-limit c to c hat of g of c hat. And this time the co-limit is formed over this under category, under C of quasi-isomorphic objects. So that's the dual formula for our derived functors. And as an example, we have that we can consider the following two functors. The mapping space functor map in Ka from A into blank. That's a functor from Ka into the infinity category of spaces. And note from now on we assume mapping spaces are actually functorial. So we're just using that functor. We also have the functor map in Ka from blank B, which is the functor from Ka op equal to Ka op into S. Then the formulas for map in the derived categories A, B. So Achim in his talk has given us two formulas for computing the mapping space in the derived category between objects A and B. And one formula was a co-limit where I resolve this variable, and the other one was a co-limit where I resolve this formula. And these just show that, maybe show up to providing the correct maps, which I don't want to go through now, show that map dA from A comma blank is just the right derived functor of the mapping space in Ka from A comma blank. Right? According to this formula, the right derived functor is just computed by exactly this co-limit. It's the exact same co-limit that Achim had on the board for the mapping space. And the mapping space dA from blank comma B is also the right derived functor of Ka blank comma B. That's just the same observation applied to this functor, blank into B. And that is, so in other words, the derived functor, the mapping space in the derived category is just the derived functor of the mapping space in the category Ka. And here we see we can either compute this by the formula that Achim has given. We can either compute this in the first variable or the second variable. And this is maybe the analog of the balancing X formulas you usually see in homological algebra. And in fact, actually, we will next time give a proof of the formula for the mapping space in the derived category that Achim had on the board. And so the proof will actually rely on the formula for derived functors that we proved this time, together with the observation that in every Dwyer-Kahn localization, we will see that next time the mapping space is just the derived functor of the mapping space in the bigger category. So what Achim had on the board is in fact a consequence of the theorem I had on the board today. And let me also note, one could also be tempted to say, I mean, this is usually, by the way, written as map dA is just R map Ka. Whereas here somehow you have this ambiguity of whether you can derive in the first and the second variable. You might also be tempted to derive in both variables at the same time. But at the moment we can't quite do that because, you know, if you look at the HOM in an abelian category, this is not additive if you let both variables vary. It's kind of additively in every variable separately. But next time we will develop the formalism of how to derive non-additive functors. And then we'll see this is also the non-abelian derived functor if you will let both variables vary. So in every possible sense is the mapping space in the derived category the right derived functor of the mapping space in the category Ka. And recall this was just given by concrete chain complex, so the chain HOM. So that's maybe the formula you usually see in homological algebra where you say the HOM or the X is just the R HOM. Okay, so now let me end this lecture today by giving you a proof sketch of the formula that I had on the board for the left derived functor. Proof sketch. So what we wanted to prove is that the left derived functor of C is given by the inverse limit. And let's make our lives easy and assume all the limits and everything exist that we need. And it's given by G of C hat. So how does this proof work? So we have to check that one subsequently follows the following steps. So the first statement is that one shows that this formula, so LGC, if we define it like this, we could just define a functor LGC by this limit G of C hat defines a functor from Ka into D. And for this you basically, I mean, in ordinary categories you would say this follows from the functoriality of the limit in the indexing category, and the same is true here. You just have to be a little bit careful. You have to use some lemmas about functoriality of limits to make this into an actual functor. So this step is the first step. The second step is that it preserves weak equivalences. And why is this true? I mean, this might be sort of morally obvious. You take just the inverse limit over all weak equivalences to C, and that this is invariant in the weak equivalences seems kind of clear by construction, but it turns out, I mean, this is a little tricky to prove. The way you prove that is you check that in that case, in fact, the slice category quasi-isos over C and quasi-isos over C prime. If you have a quasi-iso from C to C prime, these slice categories, I mean, that's an obvious pullback functor, and this, in this case, actually has an adjoint. And then you get that actually certain cofinality statement, which I don't want to get over. I mean, it just has to do with the fact that mapping out of adjunctions produces adjunctions, so the right Kahn extension will be given by post-composing with this adjunction. Again, this, I mean, if you want, feel free to go through these steps by hand, and especially those of you who already know about cofinality and adjunctions. For those, this is a heavily recommended exercise. That's step 2. Then we have step 3, and this is maybe actually immediate consequence of step 1 if you want, but there is a natural transformation. It's a natural formation eta, which goes from LG to G. And this is just given by sending, I mean, this is just somehow the map which goes to the pullback, right? So if you have any object C, then, I mean, this is a limit, and then you just project to the part of that limit which is just given by the identity. The identity is certainly quasi-isomorphism. So you just have this projection. So again, this is basically part of 1 technically, but I want to highlight it here again. And certainly, and this is for us, this is obvious, if G already preserves quasi-isos. So meaning it sends quasi-isomorphisms to equivalences in D, then eta is an equivalence. Right, this is obvious because then this is a limit over a constant diagram. And as we've seen last time, this indexing category has an initial object and, a terminal object, the identity, so the limit is just going to be the object, the evaluation at that object. So here we are using that, checking that a natural transformation is an equivalence can be tested pointwise. And then there's a 5th step, maybe I start here because this is a little longer. Now, taking together steps 1 through 4, you get a map. So you can start with maps H into LG. Right, and then you can, what we want to show is that post-composition with eta is an equivalence, map from H to G. Right, that's what we have to show to verify the universal property of the left derived functor. But then actually we can apply L to that. So we get a map from LH to LG. Right, and now the point is that H is already a functor which preserves weak equivalence. So this is what we have to check for every H which preserves weak equivalences. But that means that LH is equivalent to H. So this is actually equivalent to H. Map from H to LG, and then I can post-compose with eta. With eta lower star, this gives me map H to LG. So in principle, I've also pre-composed with the inverse of eta applied to H. And that gives me a map eta lower star after L. And the 5th step consists in checking that this is an inverse to the map eta star. So it's an explicit map. And if you think about what this means for a second, this comes down to checking actually that 2 possible transformations, LG to LG, are actually equivalent. So you can do L eta and eta L. And it turns out you have to check that both of these are equivalences. But, I mean, or homotopic. This is not too hard in this situation, but there's something to check. It doesn't follow formally from 1 through 4 that this is an equivalence, but once you also check that these 2 maps are equivalences, it follows. And that is basically the proof of my theorem for today. Okay, now I want to say a few words about adjunctions, and then to put everything in perspective, and then I end the lecture. Let us define what an adjunction is first. Let C, D be infinity categories with functors L from C to D and a functor R from D to C. So I have two functors, one from C to D and one from D to C. A natural transformation epsilon from the composite L after R. So that's an endofunctor. If I first carry out R, I go from D to C and then to D into identity D is called co-unit of an adjunction. If for a given object, pair of objects, C in C, D in D, the induced map from the mapping space in C from C into RD, right? The functor R applied to D, then I have a map, I can apply L to that, then I get to the mapping space in D from LC to LRD, and then I can post-compose with epsilon D, and so I get to the mapping space in D from LC into D. If the induced map is a homotopy equivalence. Dually, a transformation eta from the identity C into RL is called unit of an adjunction. If for every pair of objects the induced map in D from LC D, I can apply R again, so I go to map in C from RLC into D, RD, sorry. And then I pre-compose with eta C upper star. Go to the mapping space in C from C to RD is an equivalence. In either case, so if either a co-unit of an adjunction or a unit of an adjunction exists, we say that L is left adjoint to R and right L left adjoint R. That's the usual symbol. Okay, and of course, this is a little bit problematic because now we have two definitions for the same notion. L being left adjoint to R now means either there exists a unit or a co-unit. And we'll see now that this is in fact equivalent. The existence of a co-unit is equivalent to the existence of a unit, and either determines the other uniquely. And in order to say that properly, we actually invent a third definition of adjunction, which is symmetric. And then we'll see that this is equivalent to either of the two. And for this we say that given LR as above, as there, and eta epsilon, a transformation from LR to the identity, and eta from identity to RL. Then, but not necessarily units of adjunctions, just natural transformations. We say that the zigzag identities hold if the composite so I can start with L. I write this as L after identity, and then I can compose with eta. So that gives me a map from L after R after L. Right, and then I can compose in these two components with epsilon. And that gives me a transformation to identity after L, which is L. Right, I get a natural transformation like this. And I also get a natural transformation if I start with R. I write this as identity after R. And then I go with eta to RLR. Eta epsilon. I go to, I guess I apply it here, so I go to R. Okay. And so, I mean, maybe I should write R after identity equals R. If these two composites are equivalent to the identity L, respectively the identity on R. So what does this mean? So as functors in the functor category from, I guess, for example, L is an object in the functor category from C to D. And as such, we now have a morphism of L from L to itself, and we can request that this morphism is equivalent to the identity, right, as a morphism in this functor category. And we just require the existence of every equivalence. And in that case, we say these satisfy the zigzag identities. And now here's the key proposition. If epsilon transformations epsilon and eta satisfy the zigzag identities, actually I'm not sure whether I should capitalize this or not. Is this a name or I don't know. Anyway, so let me capitalize it. Zigzag identities. Then these are unit and co-unit of an adjunction. Conversely, given a unit of an adjunction, eta, then there is a unique co-unit epsilon such that the zigzag identities are satisfied. Okay, so in other words, I'm saying giving a co-unit of an adjunction is equivalent to providing a co-unit of an adjunction is equivalent to providing both, I guess, epsilon and eta satisfying the zigzag identities. And here's a proof. And I will only prove the first part of this, that every every junction gives unit and co-unit. And that is just, if they satisfy the zigzag identities, assume epsilon and eta satisfy the zigzag CZ identities, then, in order to check that it's a unit of a co-unit of an adjunction, we, for example, have to check that the induced map from C into RD, right? We have the map from C into RD. I guess this map is now L into map D LC R LD into map D LCD, right? We have to check that this map, in fact, or the claim is that this map is inverse to the map D LCD, which comes from, I guess here we have an inverse map, right? Here we have applied basically our unit, co-unit eta. Sorry, I guess the co-unit was called epsilon. And then here we go to map RLC to RD, and then we apply eta. Map D C, RD are inverse to each other. So that's my claim. And you just verify this by just spelling out what it would mean for this to be inverse to that. And then you immediately see, if you spell out the diagram, you immediately arrive at the fact that you need that this composite, both of these composites are the identities. And so once this is satisfied, you immediately get that these are inverse to each other. So in particular, eta is a unit. This is a, I guess, sorry, I get confused between unit and co-unit. That eta is a co-unit and epsilon is a unit. And for the converse, you have to work a little harder. So in order to get actually this epsilon, you need to invoke a certain version of the Yoneda lemma. So basically, kind of what you get is that the pointwise transformation you get, and then you need to sort of claim that the pointwise map you get from this is actually a natural transformation, so the naturality. And this, I guess if you know the proof from ordinary category theory, you can just assume this goes through, and it does, but this requires some technology, which I don't want to get into now. So this is, maybe I'm allowed to put a box in quotation marks here. Okay, so that's about unit and co-unit of adjunctions. And let me say one thing which is a little bit confusing, namely, a priori, this looks like a little funky here. We just somehow ask this to be somehow equivalent to the identity. It's not that we sort of put the equivalence to the identity as part of the datum of satisfying the zigzag identities. If you're used to homotopic coherence and to working in infinity categories, it would be the more canonical thing would be to somehow provide this, provide some transformation and then require further coherence relations for this natural transformation. But the fact that actually the part which I did prove is actually that once you have this, you immediately get that this is a unit of an adjunction. And then, in fact, if you somehow carefully work out how you get the co-unit, then this will automatically come with a preferred transformation to the identity, and this will satisfy higher coherence laws. So in other words, what I'm saying, and this has been really nicely worked out in work of Emily Real and Dominic Verity, so they make precise what kind of coherences you could possibly ask for. And then this little argument that I sketched tells you that actually everything we just know this is equivalent to the identity uniquely and canonically extends to a sort of coherent, say, zigzag identity thing. And as an exercise to really understand what I just said and how this coherence versus non-coherence works out, the exercise is to just check that if you have a functor which is an equivalence, then it's left and right adjoint to its inverse. And note, if you just have an equivalence, this just means there is a functor the other way and transformations not satisfying anything. So you have to really verify that you can choose the natural transformation in a way satisfying these zigzag identities. It would be one way to solve that. And that gives you a feeling for what is the difference between an equivalence and an adjoint equivalence. They are actually the same notions, but somehow you have to understand how in order to solve this exercise. And so now let me give you a bunch of facts about adjunctions. And these are mostly easy to verify once you have the correct naturality properties. So given f from C to D, then the pair R, eta, maybe I should call it L, sorry, maybe I should say given L from C to D, then the pair eta is unique if it exists. So the adjoint is uniquely determined and unique in our usual sense up to contractible space of choices if it exists. So the composite, second claim, the composite of left adjoints. So if I say left adjoint, I just mean functors which admit a right adjoint, which by the first part is unique in the appropriate sense, is again left adjoint with right adjoint given by the composite of right adjoints. And if you want, one can make this a highly coherent statement of the sort that if you consider the category of infinity categories and left adjoint functors between those, this is just defined to be the infinity category obtained as a homotopy coherent nerve of all infinity categories, and the mapping space just consists of the subspace of the old mapping space consisting of the left adjoint functors. And then, it turns out this is actually equivalent to cut infinity R op. This is the coherent statement, where here this is just the infinity category and right adjoint functors. And the equivalence is just sending a category to itself and the left adjoint functor to its associated right adjoint. So that's just the coherent version of what I said here. And this definitely requires some vibration technology to prove correctly. Okay, so that is this thing. And then the next statement I want to make is the relation between adjoints and co-limits. So if I is a small infinity category, then recall, consider the functor delta, which goes from C into the functor category I into C. The functor just given by pullback along the map from I to point. So it sends every object in C to the constant functor. I guess I've denoted it C lower blank before when I talked about the constant functor, but I think C is maybe not a good notation for a functor here, so let me denote it by delta now. So that's this kind of constant functor. Now assume that delta has, say, left adjoint. I guess I'm switching here between left and right adjoints, and by the way, the notation eta and epsilon is the opposite from what I did for left and right can extension. So for left and right derived functors. So I apologize, this is not completely standard and I'm probably not 100% consistent with eta and epsilon. But anyway, so assume that has a left adjoint L. Then for every object, every functor f from I to C which we consider as an object here, we get from the unit of the adjunction a map from F into the left adjoint L applied to delta. I guess delta applied to the left adjoint, sorry for that. Left adjoint functor, and such that the induced map from the mapping space in C, I'm just spelling out what this means in this case, from LF into any object Y into the mapping space from F into delta Y is an equivalence. But what does that mean? That means in our old definition that L of F is just co-limit over Y of F. Right? This transformation is exactly making this a co-cone under F, and then this is exactly the universal property on the nodes that we've given before. Right? So this just means once we have an adjoint, then it's pointwise the co-limit. And in fact, the converse of this statement is also true. So let me state this as a proposition, because this is actually, you see, somehow, if for every object we have an adjoint, a co-limit, then somehow we get pointwise this transformation for every f at a time. But it's a priori not necessarily clear that those can be grouped together to a natural transformation, natural in f. And so the content of the next proposition is that this is true. So assume if C has all I-shaped co-limits or I-indexed co-limits, then delta admits a left adjoint which necessarily, by my previous discussion, is pointwise the co-limit. So it's pointwise given by this formula above, because of the uniqueness of co-limits. But here's a stronger claim, namely that those group together. And that's actually a non-trivial statement. And this is in fact not only true for this adjunction, but it's more generally true for any adjunction. So let me maybe say that as well. Assume that a functor L, C to D, has for every D locally a right adjoint. So let me say what I mean. An object R, and I guess maybe I want to, now I'm phrasing the dual notion again. So here a co-limit functor was left adjoint here, but so let me maybe state the right adjoint notion here, since I discussed right adjoint functors more. So there exists an object RD with a transformation with a map from LRD to D, such that the induced map on mapping spaces for every object in C, the induced map from C to RD into the mapping space, and this is the mapping space in C, and then we have the mapping space in D from LC into D is an equivalence. Then L admits a right adjoint. A right adjoint R given pointwise by R. So this is actually a very, very useful principle of constructing functors and natural transformations, because this tells me in particular that this R varies as a functor in D. right? And this is, I mean, by what I said, not clear. For example, we've several times now used the functoriality of co-limits in this course. I mean, we've actually also used the functoriality in the shape category, but if you fix the shape category, then this at least gives you a highly coherent statement about the functoriality of the co-limit as a functor for fixed shape. Examples. And I don't want to, I mean, I could basically give you an endless list of adjunctions at this point, and a lot will come up. So let me just give you a short list and not give any proofs or provide any evidence. I just leave that as a possibly amusing exercise to you. So I first have the functor s into z given by pi naught. And this is left adjoint. This is something Achim has used in his lecture already. And I guess the claim is that the right adjoint is given by the inclusion of Z into spaces. Just you consider a set as a discrete space. The next thing that Achim has used is if you have C over X, if you take a slice category of any infinity category over any object X, you have the functor which forgets down to C. Forget. And I guess the claim is that this functor is left adjoint provided C has products. I guess you need, I mean, the right adjoint is given by just taking an object here and crossing it with X. Okay, so these are two examples of adjoint functors, and I guess I've also already seen the co-limit functor as an example. And the reason this came up in previous lectures is that we really needed to know whether these functors preserve co-limits or limits. And the general statement is the following proposition, whose proof I leave as an exercise, because it's really easy, is that left adjoint functors preserve co-limits, and right adjoint functors preserve limits. More precisely, given a co-limit cone, apply a left adjoint functor, it stays a co-limit cone. Given a limit cone, apply a right adjoint functor, it stays a limit cone. And that is really an easy exercise in terms of universal properties and effect on mapping spaces of what we've seen so far. And let me end this lecture now. I think this is my third time ending this lecture by something, but this time it's for real. So let me just end it by telling you why this even came up today. Namely, I talked about derived functors and Kahn extensions. And so let me just make that precise. Definition. Given a functor P from C to C prime, and any functor f from C to D, then a triangle I have C prime here, and I have my functor f here, and I want to extend this to a triangle like this, and maybe I call this arcan f. And now the natural transformation goes this direction. So in other words, a pair consisting of a functor arcan f and a natural transformation eta, and now I'm probably again switching the role of eta and epsilon, sorry for that, is set to exhibit arcan F as the right Kahn extension of F along P. Okay, exhibit arcan as the right Kahn extension of F along P, or short, right Kahn extension is a right Kahn extension. If, well, it is terminal in the sense given for derived functors. In other words, the natural transformation for any functor h from C prime to D, I have natural transformations from h into arcan F. The induced map is an equivalence to maps, and this is of functors C prime to D, and this is of functors C to D from H, I guess P after H into F. H after P, I guess. Into F. So that's the universal property of the right Kahn extension. And I guess this just gives a universal property for a given F. And from this formula, we see this is actually like a local adjoint here. You see, this is a locally adjoint formula. And so corollary of our local to global principle for adjunctions is the following. If the right Kahn extension arcan F exists, and by the way, this notation is abusive. Probably I should put the P somewhere, but I'm not going to. Exists for every F from C to D, then the restriction functor P upper star from functors C prime into D to functors C, D. And by the way, when I say it exists for every functor, of course, mean for every functor with fixed target D. I fix D once and for all. Then the restriction functor here admits right adjoint. Right adjoint. And this is pointwise given by arcan, so I just denote this also as arcan. Right. And of course, there's a dual notion of left Kahn extension that would then correspond to the left adjoint of this restriction functor. And we have applied that principle basically to C prime even being C adjoint W to the minus 1. And the notion of right and left Kahn extension is a little bit subtle because there's also the so-called pointwise left and right Kahn extension. So we'll say a few words about that in the next lecture. So first let me note that of course you could also ask for something to be an absolute Kahn extension, which would mean that it satisfies this. Such a triangle is not only terminal, but terminal after post-composition with any functor. That would be called an absolute left and right Kahn extension, and that's what we had in our case of absolute derived functors. You could also ask this to be somehow compatible with pullback in the C variable. And that has to do with the so-called pointwise formulas for right Kahn extension. And this will, next time when we discuss the Yoneda lemma, help us to see why this is actually called right Kahn extension. And the reason is that if somehow, this is somehow an extreme case where somehow the functor from C to C prime is in some sense surjective. Could also consider the case where C sits fully faithful in C prime. And then we'll see that for the right Kahn extension, in fact, under suitable assumption, making that pointwise formulas hold, this eta is actually an equivalence. So this right Kahn is then actually an extension of F. And that's why it's called right Kahn extension. So in the fully faithful case, right-Kant extension is literally an extension under suitable assumptions on D. That ends my lecture for today. Next time we'll keep going with the Yoneda lemma and talk about non-abelian derived functors. Thank you very much.